Okay, so today we are doing polar coordinates. So all this says is that when we talk about coordinate pairs, right now we talk about them as the horizontal and vertical distance it takes to get from the origin to a point. We call these our rectangular or Cartesian coordinates. So this is what you've been graphing since you were in, I don't know, like 6th grade. What we're going to do today is we are going to take these rectangular coordinates and we are going to transform them into polar coordinates. I'm going to show you. Oh my gosh. So when we talk about a polar coordinate system, it looks an awful lot like our unit circle. So on this polar coordinate system, I have the important angles from my unit circle, best as I can possibly draw them.
Oh, shucks.
Yeah, it's bad.
I've been drawing that too slow. Okay.
I'm going to go ahead and mark some of these angles just so we have them as a reference. So our polar coordinate system is based off of our unit circle and the angles that we have on that unit circle. Again, I'm just highlighting some of the important ones, an infinite number of angles on here. I wonder why.
That's kind of what she said.
And not only do we categorize our polar coordinates by the angle at which they correspond to, but we can also measure distances. Except each of our distances is circular in reference to the circular pattern of our graph.
Are you sure not just playing darts?
I am positive, but it does look an awful lot like a dartboard.
It's like Spider-Man. Dartboard. We're playing darts. Okay.
We can draw the best circle still. We already had that competition. We do it again? Oh, frick me.
When we talk about polar coordinates, we talk about them as their length r, comma, their angle. So this is the distance. The theta then is our angle. And I'm going to show you how we identify where a point is on a polar coordinate system here in a second once you get done drawing all of this. I love polar coordinates. Huh?
R radius.
No, that is distance.
But I was thinking the R stands for radius.
Right. In theory, you could think about it that way, but that makes it seem like we're working with a circle. We're really not. We're just working with one particular point. So when we are graphing points on a polar coordinate system, so on this graph, there are two different types of R values that I could get. So over here, I'm going to go ahead and do a couple examples. The first type of R value that I could get
We gotta draw those circles.
Is a positive R value. So a positive R value indicates that I would face the angle outlined in my point, and then the positive R says facing that angle, I'm going to walk forward R number of steps. So R here indicates a positive directional movement. It is also possible for our R to be negative, and it literally means the opposite here. So still facing my angle theta, instead of walking forward along that angle, I'm going to walk backwards along that angle. And this is true for R's that are negative. So the angle theta doesn't necessarily change. It's going to be an angle from our unit circle. The R then tells us whether we are walking forward along that angle or backward along that angle. I know this sounds really, really confusing, so we're going to do several examples to kind of get you used to it.
I feel like I'm like working for NASA.
gonna give everybody a chance to finish writing first.
I just feel like I'm mad.
The
I'm hacking.
best math class, come on.
Writing code now.
It's not the class that's
You
good.
should learn how to break code.
Well, thank you. I know, the class sucks.
Yeah.
I know this, I'm not dumb. I just hope I make it a little bit more fun.
So you always get my
Yeah.
Certain things you do.
I try.
It's not-
I try.
Like,
Okay.
shade.
So let's do an example.
She just assigned us so much homework right now.
Double the homework.
She's like, little do you know, you got 35 questions.
You don't have 35 questions, I would never.
She's like, you have 75.
You actually have 34.
Okay, so the example we're gonna do.
Or different answers.
I would never give you 35, but 36 would be an option.
I'm over 50 even if
Five,
I'm
I'm go. Oh, 5.
Yeah, we'll make it 5. It fits better on the graph. So what we're gonna do is we're going to graph the polar coordinate 5, 120 degrees.
That's a polar coordinate.
That is a polar coordinate because it gives me my distance, comma, the angle at which I'm looking at it. So if I wanted to graph this, I'm gonna go to my circle.
It's a positive 5, so that means we're going.
Hold on. Starting at 0, 0, where's 120 degrees?
Like, this one.
That
This
way.
way.
Up and to the left.
Right there, approximately.
Right.
So that's my 120 degree angle.
Right.
This number, whether it's positive or negative, tells me the direction at which I'm walking. So if I'm facing that 120 degree angle, am I going to walk forward along it or backwards?
Forward.
Forward. How'd you know, Jerry?
Because it's positive.
Because it's positive. So I need to count 5 steps out along that 120 degree angle.
I need to know where to draw the circles.
It's
Yeah.
just, They'll be- like each one of these is 1 unit, no different than having like 1, 2, 3, 4, 5 on your axis. So I walk out 5 steps, and that's where my point exists.
Is this what we need for when we're reading radars?
Stuff like this, yeah. So that would be where my point is. Does that kind of make sense?
When
Oh,
you
that's
learn math,
crazy.
You learn how to read on radar.
So we found the angle, we found the distance, and we use them together to identify where my point is. That's
Now,
part of what we're doing today.
that's what I thought. I was gonna say, now where's the catch?
Part of,
I'm gonna give you another one to do on your own.
This is cool.
Is anybody super confused by how I graph this? Does it make sense?
Yes, but are you gonna give us like 243?
I would never make you draw them.
So-
You could always count by like tens too. You don't have to count by ones.
it would say -5.
Yeah, if I wanted you to walk backwards.
I meant like 242, like.
Degrees? No, I'd always give you one directly from the unit circle.
So the negative would just be the opposite.
Yeah, so if this was -5, I would have faced 120 and I would have walked backwards 5 steps.
So
Still
are we
along
gonna
that
make
angle.
angles?
Yeah, we always stay along whatever angle is identified in my point. So I'm gonna give you one to do, then we'll move on to the next portion.
That's not too bad though. Not at all.
Wait, oh, sure.
Well,
Here's where she throws in fractions. Oh wait, that's not bad.
you just gotta convert it.
It's still just an angle from a unit circle. I can't promise you that they're all gonna be given to you in degrees or that they're all gonna be given to you in radians. I'm gonna mix it up because I think that's fun. So you can definitely just use your unit circle to identify the angle that I'm talking about.
What's 180 divided by 6? Or 180 times 5
180 times 5? 900.
divided by 6.
Divided by 6. What is it?
I don't know. That's the angle I need.
150.
Okay, so that's angle 150.
Yes, ma'am. No, not yet. She'll be back Wednesday.
What happened to her?
Nothing. She's in Colorado.
Oh snap.
Yeah, she'll be back Wednesday.
Well, she's having a good.
As long as she doesn't get snowed in.
Having a
Were we
good
supposed to get
time.
snow
It
last
is
night or-
We were supposed to get a little bit today. Oh no, they already got like 2 feet of snow out there.
Really?
Yeah, they canceled all the Denver flights over the weekend, so she's hoping that hers isn't
We
canceled.
gonna get a snow day tomorrow.
No,
Hey, there's nothing wrong with getting snowed in another state.
I agree. She's with my brother, so I guess that's fun.
Have a good time.
Huh?
How was the graduation?
Good. Yeah. Okay, are we all done?
If I make this paper ball, then the garbage can, no.
How about you make that paper ball in the garbage can, I'll knock off half the homework problems
It's
from
not,
your desk.
it's not even gonna fly that far.
Okay, we'll see. No, okay. I should have made the deal that if it doesn't go in, I double the homework problem.
No, I don't think you should.
I should have made that deal.
It's too late
That's
now.
why
I
threw
know.
it. I didn't say anything.
Okay, so I'm gonna draw just a coordinate grid, and we're gonna have somebody come up here and do a part of this.
Ooh, I should probably draw it on my paper.
You probably should. So I'm just gonna go ahead and draw the coordinate grid.
Where's my 150?
Who would like to come up and identify the angle? Okay, Zach, come on.
Watch me be long.
I laughed so hard. Okay, 150 degrees, beautiful. It should be down a little bit more, but it's not bad.
Alright.
Anybody not get that angle? Awesome. Who would like to come up and place the point? No, Zach. Boone, awesome. I love doing that.
Go back, press it back.
Go back.
I got it. We're good. We're good.
We did.
Now we gotta redo the whole.
You're so happy.
It's the last 2 weeks before spring break. I'm ecstatic.
When do I get to see your kid?
I don't know how important it is to draw like good circles.
We can't do perfect circles. There's
How
no
about
such
this?
thing, so you're fine,
Take a
honey.
trip to Florida.
That's not
bad.
Drive to Florida.
I mean, technically, any circle that's 360 degrees is perfect.
No. A perfect circle has a consistent arc throughout the entire thing. And there's no such thing.
That looks perfect.
Okay, Boone, I have a lot of questions for you. First off, how did you know how many rings to draw?
Because of the sense.
Okay, so we have to have at least 6 rings, that way I can place it. You could have done 10 if you wanted to. Also, why didn't we move forward along that 150 degree angle?
Since it's a negative, so you move away from the 150 from.
Okay, do we still stay on that same line?
Yeah.
Okay,
That's what I tried to do.
also, I love that he drew the dotted line going backwards. That way it showed that we were staying on that same straight line. I require that you do that if we have a negative. So that is absolutely beautiful. Good job. Thank you. Perfect. Who got that right? Anybody super confuzzled?
You gotta grade us on how accurate our angle is.
Absolutely.
If it's supposed to be 150 and you put it down here, yeah, we're gonna have an issue. But if it's close, I'm fine.
We're gonna throw hands.
So we're fine with graphing if I already give you the coordinate, correct?
Oh, now we gotta find the coordinate.
So what if I give you a coordinate as a rectangular and ask you to switch it over to a polar and then
Easy.
graph it?
It's gonna be easy.
Let me show you what we're gonna use to do it.
Just give us the graph, and we'll give you the point.
We gotta draw a rectangle.
Give us that. Give us that. Coordinate.
So we're gonna talk about coordinate conversions now.
I need either.
So this means changing from rectangular to polar and polar back to rectangular.
Is this the last one?
Yeah,
For
Yeah,
today,
we're good.
for today, it's all that.
we're good.
That
Okay.
extra doesn't seem comfortable.
So before we start actually showing how you're gonna convert, I'm just gonna show you some information that kind of relates it all together. So first thing is that my coordinate, rectangular coordinate x and y, when I square them and add them together, is equal to my distance r squared. Additionally, tangent of my given angle theta is equal to my y coordinate over my x coordinate. Cosine of theta is equal to my x coordinate over my distance r. And sine of theta is equal to my y coordinate over my distance r. So this is just some information that we have that is going to allow us to convert. So now we're going to talk specifically about polar to rectangular conversions. So when we are converting from polar back to rectangular, polar is in terms of r and theta, whereas rectangular is in terms of x and y. So my goal is to get x and y by itself in terms of r and some angle. The ones that we're going to use specifically are that coordinate x is equal to my r times cosine of theta, and y is equal to r times sine of theta. The example we're going to start with this one is to convert 4 pi over 3 into rectangular coordinates.
Pi.
So you're going to use your unit circle for this, and you can use a calculator for this as well. So it's already in terms of r and theta. It doesn't hurt if you want to label what your r and your theta are, just to make sure you're using the correct values in the correct places. I know to get rectangular coordinates, I need to solve for what x is, and I need to solve for what y is. It told me that x is equal to r times cosine of theta. If I fill that information in, I get x is equal to 4 times cosine of pi over 3. I can use the back of my unit circle to figure out what cosine of pi over 3 is.
60.
No, that's what pi over 3 is in degrees. But what's cosine of pi over 3?
Oh,
Go to the back of your unit circle. Hang on to that for a second. Go to the back of your unit circle. Go to pi over 3 and slide your finger over until you hit the cosine column. What is cosine of pi over 3 equal to? 1/2. Good, Morg, you got it. So that means x equals 4 times 1/2, which just equals 2.
so you can't plug it in.
You can, yes, but recognize that a lot of the values on the back of our unit circle have radicals in them, and your calculator will give you a decimal. So just be careful. So that's my x coordinate. I'm going to do the same thing for my y coordinate. Y is equal to r times sine of theta. Again, plugging in the theta and the r from above. I get 4 times sine of pi over 3. So what's sine of pi over 3? Square root of 3 over 2. So I get 4 times the square root of 3 over 2, which becomes 4 root 3 over 2. The 2 and the 4 reduce to just 2 times the square root of 3. So 4 pi over 3, when converted into rectangular coordinates, becomes 2 root 3. How do we feel about that? Not terrible. Anybody super confused, Devin? Oh, 4. Okay. I'm going to wait because we have one more example, and then I will ask for 1 to 5. Seriously, though, is anybody confused by anything we did here? Does it kind of make sense? John, are you okay? Okay. So now, since we just went from polar to rectangular, let's go the other direction, and let's do rectangular and polar. So going from rectangular into polar, we're going to use that r squared is equal to x squared plus y squared. But I don't want to solve for r squared. I just want to solve for r. So if I simplify this, I get r is equal to the square root of x squared plus y squared. And that allows me to just plug it into my calculator really nicely. I also know that tangent theta is equal to y over x, which means if I'm solving for theta, then tangent inverse of y over x is going to equal my angle. So these two bottom ones are really the ones that we're using. I just wanted to show you how we got them. And the example we're going to use is to convert 1, 1 into polar coordinates. As a refresher, rectangular coordinates are given in x and y. Polar coordinates are given in r and theta. I have a point 1, 1, which is x comma y. The first thing I'm going to solve for is my r because I think that's the easiest one. So I get that r is equal to the square root of 1 squared plus 1 squared, which is the square root of 2, and we're going to leave it as the square root of 2. But I have a question for you. What do I actually get when I take the square root of something? For example, 4. What's the square root of 4? And. So we get a plus and a minus. So instead of having r is equal to the square root of 2, we actually get that r is equal to plus and minus the square root of 2. So when we convert from rectangular into polar, we can actually find 2 different angles, which it could be. And yeah, I want both options. Okay? Is anybody confused by how we got plus and minus square root of 2 for r?
It's not a perfect square.
You just leave it like this, yeah. Okay, so now let's find our angle theta. So we're going to use, sorry, go ahead.
Does the other spots have to graph it?
You're going to have to graph them too once we get there. But they have to do other stuff. So we get tangent inverse of y over x. Both of them are 1, so I get 1 over 1, which means I get tangent inverse of 1. And from the unit circle, there are actually 2 angles where tangents equal to 1. So again, you're using the chart on the back of your unit circle. And I would like both angles. So I did here one of them, so it's going to be 225 degrees is one of them. And what's the other one, a new one other than Chandler? 45. Everybody look at the back of your unit circle. Make sure you see how we got that.
Yep, you just go to tangent 1.
Yep, just go to the tangent column, look for where it equals positive 1, and then tell me the angle or angles that make it true. Anybody confused so far? Okay, so here's the most fun part of this.
How would you write that? How polar coordinate?
I'm going to show you in a second. Here's the most fun part of this. I have 2 r's and I have 2 angles. Now I need to pair them up correctly so that my point ends up in the same place as the point 1, 1 on a rectangular coordinate system. So the first thing I'm going to do is I'm going to graph 1, 1 just so we can see what it looks like. Right? So normal graphing, I get that my point 1, 1 is in quadrant 1. So the upper right part of my graph. Right? Correct?
Yeah.
So what I need to do is I need to pair these up correctly so that their respective point also ends up in that quadrant. So I'm going to start with the angles, and then we will identify the correct distance for that. So let's say we're starting with 45 degrees. 45 degrees is in what quadrant of my unit circle?
2.
Is in the top right, top left, or bottom right?
All right.
Top right, 45 degrees is actually right here. So if that's my 45-degree angle, and my goal is to get to that point, do I need to walk forward along the angle or backwards?
Positive.
Forward, so it's going to be positive square root of 2. Then we do the same thing with our 225-degree angle, making sure we line them up correctly. So 225 is the angle I'm looking at now. That's actually down here in quadrant 3. So if I'm looking at that 225-degree angle, am I going to walk forward along it or backwards to get to this point?
Backwards.
Backwards. So this one's going to be negative square root of 2.
Oh,
And then we're finished.
right on.
So the hardest part is just pairing up your angle and your distance correctly to end up in the desired location. You are doing questions 1 through 14 on the homework. There's graphing, there's converting, there could be a mix.
We have so much.
Okay, if you have questions, of course, let me know. Tomorrow, we're gonna do something else.